Thank you everyone for joining this early morning for our session. I hope that your day is going okay, and we are going to make it even more interesting, hopefully, with this webinar. So we had a couple of webinars before, mostly concentrating on ICHM7, on how to make an assessment, how to perform expert reviews. And we did rely, or at least Suman was mentioning the databases which are used in these activities, but we never talked really about those databases. So here we go. Today we're going to talk about multi-case databases and how we use them to support our data assessments. There are a couple of topics which I would like to cover. They're all in these slides. Start with basics. Why do we need the databases? The question seems to be obvious, but nevertheless needs to be answered. And following with what consists of our database, what kind of companies do they have, how do we get the data, how we build our databases, what is available to our customers, and finally, how we actually using the databases for our work and how we suggest them to be used. So, why do we need the databases? Well, first and most obvious and historically very original reason is to train statistical QSR models. Statistics, well, as it comes from its name, should work with some data. And when we're dealing with QSR models, we need to acquire some data before we even attempt to build a model. So that's where databases are coming, and they are very handy in that. To validate rule-based models, it's not enough to have a rule. Well, it's good to have a rule which says a nitrosamine is mutagenic or aromatic nitro group is going to cause mutation. But if, for example, you are saying the same thing about aromatic amino group, you're probably going to be wrong, at least in 40% of the cases. So rule-based models need to be not only developed, but also validated with real data. And that's where the databases would be very handy. And finally, to support case author assessments, expert review is everything. Well, again, it was a subject of multiple webinars, and we keep mentioning that, okay, it's very nice to have both statistical and rule-based models. It's very good to use them both properly according, let's say, to M7 guidance, but the recent trend is you actually not required, but recommended to expert review every QSR assessment. And you simply cannot do it without data. You need to look into additional data. You need to look into data, at least, which are supporting those models, and ideally into some analysis. And then that's what helps you to make the expert review. So our databases usually have several major components. Since we're all dealing with chemistry, of course, chemical substances will be one of the major components, and that will involve chemical IDs in form of registry numbers, RNs, PubChem CIDs, ChemSpider IDs, Campbell IDs, or something similar. Of these first two, RN and PubChem would be the main one which we're using. Chemical name, obviously, curated chemical name. I will tell a little bit later how do we curate. And structure in form of smiles code. It also needs to be curated. It's good to have substances, but if you want to build some form of QSR model out of it, the substance needs to be affiliated with some form of activity. Bacterial mutagenicity, carcinogenicity, LD50, or anything of this kind. So we do maintain records, and this actually would be the major piece of the major part of our database. We do maintain experimental records for various endpoints, and we normally record species, conditions, for example, strain, solvents, concentrations. If metabolic activation is used for this particular endpoint, then metabolic activation as well. GLP status is very important. Purity is not mentioned here, but we started to record the purity because, again, when we're dealing with bacterial mutagenicity, one of my favorite topics, it's very important to know how pure was the compound which you're using as a learning set compound. If it was not very pure, then what you're actually measuring, you don't know if it is caused by this particular compound or by those impurities which are present. And of course, the outcome. It's good to know that the chemical was tested. It's even better to know what was the outcome of this test, positive, negative, or maybe exact values, LD50 or anything like this. Finally, it's very good to have these two pieces of information, but when someone will ask, okay, How do you know that this chemical is positive in this particular strain, in that particular conditions? Where did you get this data? We obviously need to provide a publication. So we maintain reference data, authors, titles, year, volume, issues, pages, and quite frequently we also have access to the abstracts. So abstracts are part of our list of references as well. What we cannot provide PDF files for obvious reasons, copyrights. Sources of data, how do we get all those things? I provided just few which would fit into one slide. I probably can provide 5 pages of those sources. So left side contains databases which contain both structures and toxicity. Of those, the most popular, at least the most useful for us, these first 2 or 3, PubChem, ChemID+, ChemSpider. They contain various toxicities and they have definitely structures in all forms. Very important source for bacterial mutagenicity data was a division of genetic and mutagenesis from NIH Japan. That was a source of compounds within QSAR project for which we actually have a publication. And a lot of databases from Japan. Also, ECA database recently opened up through eChem portal, which allows to download and use a lot of data, very important source. EFSA database, little bit smaller. And for pure toxicity, we used FDA drug safety database, RTX, and pretty much everything what is listed here. Unfortunately, some of them are already discontinued, which is a minus. And we cannot, of course, rely only on the databases. We absolutely have to use reviewed literature. So this is part of our data assessment as well. What is the normal flow of data when we start just building our databases? We need to get to the source of the data. It could be database, publication, it could be one of those assays which are recently very developed, TOX21 or PubChem assays, very good source of data. And then we need to come up with establishing a relationship. If it's coming from publication, it could be drawing to ToxData. Sometimes it's just only name and the outcome is provided. So chemical number 1, let's say benzene, has this particular value of toxicity and aniline has this particular value of toxicity. What if I don't know what is the structure of benzene or aniline? Or sometimes, and this is usually happening with PubChem assays, only CID is provided. CID is PubChem chemical ID. CID and type of outcome of toxicity. So a lot of data needs to be filled in. So how do we do that? When we deal with publications, we are dealing mostly, quite frequently, only with drawing. I cannot say that every publication does drawing, but many of them do. And it has its advantage. So at least we don't have to guess. When this particular publication says that these chemicals are toxic or have particular values of toxicity, we know exactly which structure was used for every type. We don't need to guess. Only thing which we need to do, we actually need to make this structure computer readable. We need to quite frequently just redraw it, which is in a way a disadvantage. When you have to redraw 100 structures, that's time consuming, and the most important thing, it is an error prone. When you're drawing for 8 hours per day, you probably will make a mistake. You will put an extra bond. You will forget to put a bond. You will forget to label atom as oxygen or nitrogen. Something will happen. More easy case is when the names are provided. So we have a table with a list of names, and in the second column we have some form of toxicity data. Well, there is advantage because this kind of data allow some form of massive automated processing. And most likely we can find structures from those names under condition if the name is proper. Quite frequently the names are abbreviated in all kind of way. Or there is a technical ID instead of name, some kind of IP 346. It doesn't mean much. Or the name is simply truncated. For historical reasons, many people don't like or cannot put long names. So, for example, they would truncate 2-chlorobenzene into this 2-CL benze. If I will perform some form of automated search using this 2-CL benze, I will not find anything. So these names need to be curated. And that would be a disadvantage. Most of these curations are happening in a way or in a manual way. And we also like to harmonize names. So for example, in this example, we would choose 2-chlorobenzene over chlorobenzene 2-. And another disadvantage, we still need to get a chemical structure. So this task will turn into 2 steps. First, we need to clear the names. We need to be sure that the names which are provided are readable, are recognizable, and can be used for search. And then we actually use them for search. So for this purpose, actually, in our internal databases, we keep all possible forms of names which were historically provided over the time. Since we're doing it for like 20 years, our database is quite big. And that helps a bit in this search, but not always. So every time, in a way, it is an investigation. Every time it is a challenge. Finally, when we have a table which connects registry number or CAS number or PubChem CIDs with ToxData, which would be clear case, for example, for PubChem assays, for Tox21 assays quite frequently, but mostly for PubChem assays. Tox21 assays usually come with structures. Again, there is advantage in that, especially in case of PubChem assays. Sometimes they can be huge, up to 300,000 chemicals. And each one of these chemical is designated as a PubChem CID, and no name, no structure, no anything. We actually can find the structure using this information. Of course, the ID has to be proper. It could be a situation that one chemical will have multiple registry numbers or CIDs. It could be a situation that registry number which is provided is either discontinued or simply wrong. There are particular rules for validation registry numbers. Not everyone is using those rules, and sometimes it's simply simple mistype. And people just want to type 2 and type 3, and then that makes a registry number wrong, completely wrong, not usable. And disadvantage in here, okay, we can clean up a registry number, we can use CIDs, but we still need to get chemical structures. And another disadvantage, ideally we need to get chemical name. If our database, our model and database will say that the chemical with CID 1983 or with registry number, which is listed here, is, for example, carcinogenic, it will not tell much. But if you know that this is Tylenol, then you actually have more information. So the names are, in a way, is decoration, but it's still very important piece of information just to increase the transparency of our databases and models which were built with their help. So the challenges here, as I mentioned, multiple registry numbers. Here is an example for Tylenol. This is a screenshot from PubChem. One registry number which is actual, used by multiple sources here, and few depreciated CAS numbers. And I've seen examples, for example, when this CAS number was provided with extra 0 in the end. So instead of -2, you have -20, which will make it a wrong CAS number. And in an example of multiple CIDs for the same structure, for example, phthalocyanide, green G, it has 3 PubChem CIDs. So if you have each one of them in your table of activities, you most likely retrieve 3 identical structures. And how do we solve those situations? We need to produce a correct registry number. So we have internal routine which verifies if those rules which are specific for CAS numbers are observed, so if this number is correct or not. We also have databases which hook up chemical structures with registry number. If no registry number is available, then we use the best PubChem CID which is available. And in this case, we would use a smaller number versus bigger number. And after we have all this, if we did not retrieve structures using our internal database, we actually have to use something else outside PubChem, ChemID, plus or ChemSpider, and search them by registry number or by CIDs. So if we have everything, we still need to do some curation. So we have now something which we call chemical entity. We have some form of ID, registry number or something else, We have a name and we have a structure. The final step would be to ensure that the name corresponds to registry number and structure corresponds to both of them. So we need to have a like three-way relationship, and we need to ensure that everything corresponds to each other. Ideally, we like to use chemical structures obtained from three independent sources. Well, I mentioned them in my previous slide: PubChem, ChemID plus ChemSpider. It's not always possible, but that's an ideal situation. We have to identify inappropriate structures. Quite frequently, some sources do not pay attention if the structure which they provide is a salt or neutral form. Sometimes it is important, sometimes not. But if you have a toxicity for acetic acid, and instead of that you are putting structure of sodium acetate, it's not actually very correct way of doing things. And finally, well, obviously there are tautomers. Sometimes there are multiple tautomers for the same structures. So there is always a challenge, which structure to use. We're trying to use at least the same type of structures. I call them the less exotic type of structures, and we're trying to use them consistently. There is a challenge, existing challenge. It comes from the limitations of SMALS notations. You cannot really correctly code chemicals which contain organometallics. Coordination compounds and anything like this, you cannot really chemically correctly to code them. So we have to come up with some kind of homemade solution, and some examples are here. We just connect those metals by covalent bond. Otherwise, all those structures would just look like mixtures. And for example, if we take ferrocene, this will be a mixture of pentadienes, two pentadienes, and one iron ion. And if we'll just test them separately, it's not the same thing. The property of pentadienes in ferrocene are very different compared to isolated pentadienes. So we decided that we rather connect them in obviously chemically wrong way instead of skipping those structures or using them piece by piece. We don't use many tools in curation of chemical entities. What we use is kind of homemade tool. We take a SMALS code and strip it of all stereochemistry and salts and charges. We call it SMID, like SMALS-based ID. It is helpful to decide when we are dealing with a group of chemicals which have the same origin, because SMID essentially will leave you a skeleton of the molecule. And in case of acetic acid versus sodium acetate, SMID or skeleton will be the same. But if someone, for example, will provide the data for something which they call, let's say, potassium acetate, but after we process the SMALS code and we receive SMID which has extra carbon in it, so it's a derivative of propionic acid, we obviously will be able to catch it up right away. We also use InChIkey for various purposes, for structure comparison, for identification of duplicates and tautomers. It's for tautomers, it's especially interesting. InChIkey most of the time is identical for various tautomers. So if we have a situation when we have linguistically different SMIDs, SMALS codes, but the same InChIkeys, that's a clear sign that we are dealing with tautomers, and we need to make a choice which quite frequently goes through manual review. Manual review still takes huge part of this project, and it's very important. So we cannot completely rely on automated tools. We still have to review everything manually. And partially the reason for that, public databases are good. They are not 100% correct. This is one of the examples. I'm sure each one of you who is dealing with public databases probably met a couple of examples like this. Well, this one particular says 10 nitro, etc., naphtha, etc. Do you see any nitro group in this picture? I don't see it. So one of these is wrong. It's either not nitro or the structure is wrong. Well, so we did our big part. We curated our structures through those long and tedious efforts. But here we have even bigger challenges. We quite frequently need to curate toxicity data. And the major challenges are here. First, and most frequently one, we quite frequently have contradictory data coming from different sources. Example, this chemical tartrazine, for example, it comes with a positive and negative reports related to mutagenicity in TA98 strain. So which one is true, positive or negative? We need to decide it. We need to look into the data and decide. Or when we're dealing with so-called continuous activity data, which is not just yes or no, positive, negative, active, inactive, but its exact value, like in this case, EC3. Well, take organole. Well, the range is between 4.9 and 100. So which one to choose? And finally, these first two cases are fairly okay. We're getting those situations from the databases. The data are tabulated. The data are fairly easy to proceed and review. And at least we have structure. We have some form of label for activity or value for activity. We have those things. We just need to make some decisions. What if we don't even have this kind of toxicity data? What if we have just raw text, like for example, FDA drug labels? These are PDF files with text. And we need to text mine them, and we need to get activity values or terms out of those texts. I will talk about this a little bit later. So what do we do in case we have contradictory binary data? Well, one of the thoughts is to do a conservative approach. That means if you have a single positive call, that it's positive. We think that it makes sense if the data are coming from the same source and are measured or obtained under the same experimental condition. Then yes, sure, you made 3 experiments, one of them is positive. It would be safe to call the overall outcome positive. You change something in experimental conditions, positive, negative might have a different background. If it's coming from different sources, for example, from different papers, from different databases, we prefer regulatory sources and or GLP data. For obvious reasons, regulatory sources quite frequently perform, they are curated internally. GLP data, at least they are reproducible. Quite frequently they come with experimental details, so we actually can review them and make our own decision. If no GLP data are available, we would prefer more recent data over legacy data. There are a lot of papers pre-80s. Everything was different back then. There were different techniques, there were different criteria. Even for bacterial mutagenicity, quite frequently, there were different thresholds for deciding what is positive, what is negative. We saw multiple times then the same chemical which was tested fairly recently after year 2000. First, it's clear, it's more pure, and then it gives different results, and quite frequently positive turns to negative or another way around. So we prefer more recent data. And of course, we cannot just rely on the simple date in a publication or in some other things, on the status, on the label, GLP, non-GLP. If we have to switch the call, if we have to make a decision between several calls, it's manual review again. For example, for this AIMS results for tartrazine, we have data for TA98, which says it is positive, and it's based on a paper from fairly recent 2004 and 2 regulatory sources. And we have a historical result which is based on a paper from 1984 and 1 regulatory source which probably is relying on that data. After reviewing both papers and source sources, we decided it's positive. But if we just use brief algorithm like easy solution, probably you can say, oh, well, we have a recent paper, it says positive, and we have 2 regulatory sources, probably we should go with this call. So the manual review would be fairly quick. If we have a range of toxicity values, then the task is really challenging and very not trivial. Well, the easiest case is when the variation of values is negligible. Well, it's almost the same, plus minus 1%, 2%, 5%, if we're dealing with percentages. Then we choose the most toxic value. We go conservative way. If the variation of values is very significant, then we have to go deeper. We need to get into the original sources of each value, meaning the paper which actually measures this value, not the paper which refers to that paper. And we give preferences to well-documented GLP or regulatory sources for the reasons which I already discussed. And depending on the type of the original value, we either choose conservative values or median values. And the final call is decided after the manual review again. And as an example here, this situation with organole with huge range of values. we cannot use any kind of simplified procedures. We cannot use average. We cannot do something like that because the range is too big. So we had to review all the original sources. And after we review the sources, we found that there is a value which comes up very frequently. And we decided that that would be the best way to go with median value, which is 12.9 in this case. It's very tempting to go to simplified procedure in curation of data, especially when you have thousands and thousands data points in front of you. But it's very dangerous too. What we do before choosing the most toxic value, if we decided to go the conservative way, we still need to review the original source. If, for example, we would refer to the paper which simply mistyped the units which were used originally and mistyped it in the wrong way, we actually can introduce false positive in this way. For example, someone used micrograms instead of milligrams, so another way around, and original values was using micrograms. And we rely on later report instead of going for original report, we will get a wrong value. And in this way, the automated way to choose a conservative value is not a very good way. It needs to be reviewed. If we decide to use the average value, we need to ensure that extreme values are correct. One of them at least correct. In my case of example of organometallic, between this 4.9 and 100 values of EC3, at least one of them is doubtful. It cannot be that both of them are correct. And it happened to be that 100 was wrong. And for this particular reason, we very rarely use average value. It's a very easy way to introduce. It's very easy to do. You just make an average. In this case, you will have probably close to 50% EC3, but it's very far away from the median value which we actually use. Median value has its own caveats. We need to ensure that the most frequently reported values are based on the different sources. For example, if you have data and there are multiple reports and like 20 of them and all refer to the same value, but if we look into those reports, into those papers, into those databases, each one of them refer to some very old, very original paper which actually has this value. It's good if it is the same value, but in reality, there are not 20 reports, it's only one. All those 20 reports essentially means that this value was coming from only one source. So it's not really a very frequent value. Worst case, when those 20 reports would refer to a wrong value. It happens, we saw it happen. Someone published something in 60s, then people started to refer to this paper in 70s, in 80s, in 90s, and some of them just mistyped, used mg per liter instead of microgram per liter. And this mistype started to propagate because papers referring to each other. And that will cause a mistake. And if we'll try to use this to detect the median value, those artificially propagated wrong value, we'll get a mistake as well. So the fun begins when we actually start retrieving our data from the original reports. This is a work which was recently performed and completed by one of our employee, by Monica Giraredi, as a part of cholestasis project. When she was dealing with raw labels from drug safety FDA database, which is essentially a collection of PDF files connected with drugs which are currently in US market. As you can see, there are multiple steps, some of them trivial, some of them not. For example, you have to use some form of natural language processing when you start dealing with extracted data, when you need to obtain sentences, you extract words surrounding the endpoint term, certain depth of this extraction, 8 words before and after, identifying the keywords. There is a lot of work, and this work is not trivial. So with my big respect to Monica, this is a very huge work. It came up to be very nice, but I would not envy anyone who is trying to deal with text original reports. It's a lot of work. Finally,
Roustem, apologies for interrupting. Let's give it about 10 more minutes.
Fine, okay, we are almost there. The database which are currently available. Bacterial Mutagenicity Database is available to our customers as part of our consolidator. I will not read the statistics of the slides. You will have a chance to read it from the handouts. As you can see, there are a lot of chemicals in there, a lot of experimental data, and this database was built and curated together with US FDA. Standard protocols, everything go by OECD 471, standard strains, and typical metabolic activation types and test methods. Everything which does not fall into standard strains will still be recorded and reported, but it will not affect the final call. And by the way, the final call in the database, if it's positive in one strain, it's positive in, at least in TA100 and TA98. If it's negative in TA98, TA100, then it is negative. In some of the models which we built off of this database, criteria to be negative is negative in all 5 strains. And this is information how experimental records between the strains are split. As you can see, we have almost equal shares of important strains, T100, 15, 35, 37, 98. We have pretty good amount of E. coli data, and we still have an amount of work to do. So OECD 471 strain means we know that these strains follow the guidance. We don't know which exactly strains were used. We need to go after original publications and find it out. Another database which we used, it's Rodent Carcinogenicity Database. It's also part of our consolidator. It is in version 2. It's slightly smaller than Bacterial Mutagenicity, but it's still significant. And again, it has a support from FDA. And based on standard guidance, we use rodents, mice, rats, hamster, guinea pigs. Of course, the most prevalent are mice and rats, typical. And data sources are ECHA database, NTP, CPDB, those classical sources for rodent carcinogenicity. And we're still working on updating these databases from additional sources. And recorded experimental details are typical for this kind. We need to know species, we need to know the duration, concentrations, and type and place of cancer. I will not read this slide. It just lists that we actually have similar databases for a variety of the endpoints which are listed on these slides. So every time when you use a model along this list, you actually have a database support. And that will look like this. For example, if you want to know why a particular learning set is called positive or negative, you right click on it and you will receive this screenshot with all details. What kind of positive data we have, what kind of negative data we have. So that's how it would support statistical models, and how we would use our databases to build the models probably is going to be subject of another webinar, hopefully a couple of months later, because that's really, it's an important subject, but it cannot be briefly discussed. It needs to be discussed in details. In the meantime, that's an example how we validate rule-based alerts. So this is aromatic amine, and that's the statistic which we could not obtain without having underlying data. And that will affect the performance of this alert. In this particular case, 71% of chemicals containing this alert are bacterial mutagens. So that would be the validation results for this alert. A few case studies. So case study number 1, we have this chemical. We tested with statistical model, with rule-based model, and consolidator, which is our expert review assistant tool, gave a preliminary conclusion, positive. Why? Let's have a look. It identified the alert, aromatic amine. It gave us 3 analogs which contain this alert from the underlying databases with measured alert environment similarity. It's situation around the alert in the query compound. So query compound does not have anything in order. We don't have anything in order position here. We have something here. We don't have anything here. And that's how it works. It pretty much estimates the substitution patterns. We also have most similar analog detected by read-across. It is positive. And pretty much there are no doubts this chemical should be positive. And when we check the experimental results, it's actually aims positive. Second case study, this particular compound, we have a conflicting results here. Statistical method says it's negative. Rule-based says it's positive. the consolidator says it's positive. Let's see why. So we have a most similar analog, read-across analog is negative. Okay, we have analogs for identified alerts. They are positive, but looking at the alert environment similarity is not very impressive, especially that one. And this one is a clear example of the analog which has nothing to do with our query compound. We also have a mitigating factor here. We have this substructure highlighted in kind of bluish color, which present in our compound and known to be present mostly in Ames negative compounds. And we believe that that would be a very important factor which help us to decide that our alerts are not in a proper context because they contain this mitigating factor. The analogs which are presented to support this alert do not contain this factor here. So it's not the same. So these analogs are rather not relevant in our particular case. That leads to conclusion that the alerts are not in proper context. They are deactivated, and the amino group should be deactivated due to presence of this functionality. And this chemical is actually negative. It's class 5. And when we check the experimental status, it is actually Ames negative. Last case study is this particular compound, which again gives us contradictory results. Let's see what we can do with it. That is actually interesting case. We have a very close similar analog, which is negative, very close. Similarity is very high. The only difference is it doesn't have a bromine here. We also have very strong mitigating factor. It's actually para substitution or substitution towards a nitro group actually deactivates this nitro group. Then we have analogs which in this particular case alert environment similarity is misleading. It's very high, yes, but when we look into our chemical, this nitro group is surrounded by something else. So it's not really very relevant. So the conclusion is, based on very close similar negative analogs, we would rather conclude that this chemical is negative. And to emphasize on that, we checked the status. What will happen if we put a bromine in para position to amino group? Because this potentially could be another reason for mutagenicity. Para-bromaniline is negative per experimental data. So it's having extra bromine here compared to our analog should not make this amino group mutagenic. Final call, it is negative, class 5. And so happen to be that is in reality, it is Ames negative. When we do expert review, we also need to know what is carcinogenicity status. And that's what you usually get if your chemical is found in the Rodent Carcinogenicity Database. You get this kind of information. So it will help us to decide that this chemical might be actually ICHM7 class 1. And finally, we sometimes rely on read-across evaluation, and obviously it needs to be supported by a database. And when we do that, we will receive, for example, 5 closest analogs. One of them is exact hit. We will get a similarity value here. We will get activity values, and we'll get weighted average activity values. In this particular case, it is this value. It would not be possible without having underlying data attached or used for this assessment. We also support with our databases other projects and other functionalities, but it is too soon to disclose, and there are a lot of projects in progress. So stay tuned for our future webinars, and you will know everything about this. And with this, thank you for your attention, and I'm ready for your questions.